the people at BARC are very interested in this possibility and will follow up. I'm not going to give you any of the much of the details of it, except to say that the salt, molten salt, carries both the fuel and the breed stock. And they're separated for technical reasons, so that it's a two-fluid reactor, and one is used to cool the other, but in addition, the excess neutrons above what's needed for a chain reaction is used to convert what is not fissionable into something that is fissionable. The advantage of doing this, as was pointed out, is you can burn 100% of the thorium, extract 100%, whereas today we're only extracting 1% of the energy from uranium. So if you were to use uranium, natural uranium, it would only last 4 years, okay? But if you can extract 100%, it will last 400 years. And thorium is 4 times more abundant than uranium, so it could actually last, if you were willing to find the last bit of thorium, over 1,000 years, 1,600 years, okay? Once you can do that, all you have are fission products, and you only have to bury that material for 300 years, and it would decay down to background. So 300 years, one can ask, does one have technology where you can assure you can keep things safe for 300 years? And the answer is yes. India had that technology 5,000 years ago. You recover artifacts all the time that have been buried for 300 years, okay? So that's not difficult, all right? This is not my insight. It's really Dr. Baba's insight. Okay, however, how do you make it economical? And here we have a direct connection with solar thermal, all right? Solar thermal, as Dr. Kumar mentioned, uses the sun to heat molten salt so that at night you have hot salt, but you don't have sun. You can turn it into electricity. However, electricity is usually turned by, let's say, vaporizing water into steam, letting that steam turn a turbine. A much better way is a new kind of turbine, all right? And this is something that was invented by General Electric using supercritical carbon dioxide. What is supercritical carbon dioxide? Well, carbon dioxide, of course, is what you get if you combust a fuel like natural gas or coal. You get CO2, it's a gas. In supercritical carbon dioxide, the carbon dioxide is at a high enough temperature, above 400 Celsius, and at a high enough pressure, 100 times atmospheric pressure, so that you lose the distinction between gases and liquids, i.e., supercritical carbon dioxide can expand like a gas, so it creates a flowing fluid, but that fluid, instead of being very rarefied, has almost the density of a liquid. So imagine the power of a turbine on a jet plane, which expels and exhausts 100 times denser than air. That's really the technology. So here is a turbine that GE built. They hope to have a full working system by next year, so it's not something that's pie in the sky. And other groups are also working on. This is a meter stick. So it's something that I could hold in my hands. The inlet and the outlet is also something I can almost encircle my hands. It's much less than an airplane turbine because air is much less dense than a liquid, especially if you fly in the stratosphere. So this turbine can generate 10 megawatts of electricity. So I ask you, how does it compare with a wind turbine? Well, a wind turbine of 10 megawatt electricity capacity has not yet been built. One, the largest that has been built is over 100 stories high, all right, and has 3 megawatt capacity. So something like this can obviously beat a wind turbine. It's steady. It doesn't depend on wind. It just depends on having hot salt. That hot salt can come from solar thermal, but it could also be the hot salt in the blanket of a nuclear reactor. So it's going to be cheaper than wind. Wind is now almost competitive with fossil fuels, so it's going to be cheaper than fossil fuels. And if you make your best guess, you will be able to generate dispatchable electricity. That means electricity when you want it, when you need it, at perhaps half the capital cost of coal and natural gas. Okay? So that's a hope. It'll be so good that you, you would be, incorrect not to use it. All right? If it's safe to have nuclear power of this kind. So let's talk about safety, all right? Everybody knows about Fukushima having terrible problems because it was overwhelmed by a tsunami and all the backup to the electric power. The power lines got knocked down, the diesel generators were flooded. So they came down to chemical batteries, which they had to open and close valves to keep the thing safe. Well, any of you who has run a computer knows that chemical batteries only last a few hours. And after that, they were defenseless. They had what's called a station blackout, and the fuel got hot, the reactor shut off, but you still had decay heat, and that was enough to melt the fuel rods, and then the water that touched it turned into hydrogen, and oxygen was dissociated. The hydrogen was what they needed to release, and they couldn't release it anymore when they couldn't open and close the valve. So there was hydrogen explosion that wrecked the reactor and wrecked the environment. Now, it always puzzled me why nuclear reactors use chemical batteries. Why don't they use nuclear batteries? What are nuclear batteries? Nuclear batteries are just things that have a heat source that keeps something hot, and then an outer wall which is cold. All right, and then you put in two kinds of materials, it's like the terminals of a battery, which are different materials. So it could be lead telluride, which has 10% efficient, silicon germanium, which is 0.2, or ultimately graphene might be 0.5. That's more than enough to run pumps, to do everything. Okay, so if you really want things not to run out, nuclear decay is good. And if nuclear decay, of course, ran out, then you don't have a problem. So it's impossible to have a station blackout if you use this kind of design. And that's the basis of the safety, first line of defense. All right? Those of you who know something about thermocouples know that if you have a hot thing and a cold thing, you can, using the right material, generate a voltage drop. And if you have a voltage drop, you can draw a current. Okay, it's as simple as that. It's used in space in this way. We built thermocouples in our own work, so we know it can be done, and we know it can be cheap. No moving parts, so there's no moving parts to fail, all right? It's called the Seebeck effect. So it's impossible to have a station blackout, therefore, no Fukushima. Nevertheless, what happens if you have something really dramatic, which is a loss of coolant, all right? You could lose the coolant. We use molten salt in a pool to cool the fuel salt after it's been shut down. No more chain reactions are going on. So what happens in that case? Well, you automatically build under the reactor. This is not my idea. This is Oak Ridge National Lab's idea 60 years ago. But they had very low power, so it was very easy to build such a freeze plug. Once you go to high power, like a commercial reactor, you have to ensure that the freeze plug will melt. But in some sense, you don't have to worry, because if it doesn't melt, just wait a while. The decay heat will get larger, and you will melt the freeze plug. At that point, it will just drain by gravity. See, these are all fail-safe devices. You can worry about electricity stopping, but you don't need to worry about hot things melting frozen things. And you don't need to worry that gravity is going to fail. So it will just drop to a spherical tank where you keep buffer salt. And this is the history. This is a theoretical calculation. We're not allowed to do this kind of experiment in Taiwan. But it's a theoretical calculation. Basically, the fuel inside a tank that's been chemically kept clean so that you can breathe will rise in temperature until when it drops, it just solidifies because you have extra salt in there that distributes the heat more uniformly. It rises until it melts. At that point, latent heat comes in, namely, you need energy release to drive the frozen state into a molten state with the temperature not going higher. Once you've melted everything, you can again go above the melting temperature, and we've designed things so that it doesn't cross more than where concrete would be destroyed, all right? And then the decay heat is always dropping, so it's very important to keep things under control for on the order of a day or so. Once it's a day, it won't go any higher, it'll drop, then you'll reverse this path, you're up here, in time, it'll slowly freeze again. And then it takes a long, long time to solve the further decay. So this is our design, and you can say, well, now you have a bunch of frozen salt in these tanks. How do you get them out of there? Well, it's very simple. This is cooling by what astronomers call black body radiation. The walls of the tank is radiating radiation, and you don't need to worry that black body radiation will fall. It's what won Planck the Nobel Prize. It's not going to fail. So you just block that blanket, put a blanket that won't let radiation pass, then the decay heat will bring it back up to melting. At this point, it's perfectly safe. You drain it, and after 2 weeks, the accident is over, okay? So because Fukushima did not have this kind of safety device, you know, it's now, what, 5, 6 years after the accident, and they're still cleaning up. Here, after 2 weeks, you would be back online, okay? Longest, so it means no operator decisions. Whenever you have humans in the loop, or even computers, they can make a mistake. But physics, good physics, doesn't require it. So it's walk-away safe by physics, not by today's standards, which is called defense in depth. What is defense in depth? Defense in depth is if you absolutely must have a piece of equipment, then if you go in space or you have a nuclear reactor, people will require you to build multiple copies. So instead of one, you have to build 3 or 4. 1 knocks out, 2 kicks in, 2 knocks out, 3 kicks in, 4 comes in, 4 knocks out, well, you have an accident, right? Or you lose astronauts if you have in space. So that can only decrease the probability not to 0. Okay, it can become very small, but people are unhappy with any probability of a nuclear accident. It's impossible to have a nuclear accident. You see, we build these things in the form of a sphere. Suppose a terrorist comes in here and shoots a bazooka at this spherical tank. By definition, a sphere has the least radiating area for the volume. So when it spills out, it will have even more radiating area, and it will cool even faster. So it may destroy the plant, but the fuel